We present GRUBERT, a GRU-based method to fuse BERT hidden layers for Twitter sentiment analysis. Let's get started and define what Twitter sentiment analysis is. So we define Twitter sentiment analysis as the task of classifying a tweet as either positive or negative. Of course, the major issue that arises while doing this is that tweets often use very informal language. For example, here's a tweet which makes heavy use of abbreviations and phonetic misspellings. This tweet uses an onomatopoeic interjection and a typo. And this tweet here uses several stylistic misspellings. So assuming that you don't have the time or resources to train an embedding layer on this informal language, the question is, how do you use a pre-trained language model, which is typically trained on formal text, to perform well on the downstream task, which includes very informal text? The embedding that we use to study this is called BERT, which stands for Bidirectional Encoder Representations from Transformers. As the name indicates, BERT is a transformer-based pre-trained language model. The one that we use is called BERT-base, and it's pre-trained on Wikipedia data. BERT has been known in recent years to achieve a very high performance in many tasks, and it allows fine-tuning for different downstream tasks, which is one of the main ways to deal with the data for the downstream task being different from the data that the BERT model was pre-trained on. The BERT-base model essentially looks like this, with 12 hidden layers for embeddings. And different layers have been shown to contain different linguistic information. For example, the initial layers often contain more character-based features, while the middle layers contain syntactic information, and the final layers contain a lot of semantic information. The question then arises, which layers should you use for a given downstream task in order to achieve a high accuracy? And it's unclear which layers to use for this, or which layers to fuse together, if any. The approach that we decided on is to group consecutive layers together and then use GRUs to find the best combination of the groupings. And the reason we use groups of consecutive layers is to keep the sequential flow of information between groups. So we hypothesize that consecutive groups, such as groups 3 and 4, contain similar information that can be combined well together, whereas non-consecutive groups, such as, for example, groups 3 and 11, cannot contain very dissimilar information and cannot be combined easily. Another reason why we use groups instead of having a single BiGRU where we input all of the 12 layers is to avoid overloading the capacity of a single BiGRU. So by having, as in this example, 3 groups of 4, we have 4 BiGRUs and each one is handling 3 layers of BERT. And of course we can experiment with the group sizes. So this one has 4 groups of 3, but you can also have, for example, 3 groups of 4 or 2 groups of 6. So with this basic framework established, let's see how our model looks like. So the first step in our model is to cut every tweet to 40 tokens and then feed it through the BERT language model, which gives us the 12 BERT hidden layers. Once this is done, we use GRUs to fuse the BERT hidden layers. So here in this example, we have 3 groups of 4 and 1 BiGRU per group, which we call the embedding BiGRUs. And of course, for the groups, we try sensible combinations of fusings. So we use group sizes which are a divisor of 12, and of course each group contains consecutive BERT hidden layers. And this step can be seen as an embedding combination step to find a combination of the BERT embeddings which hopefully performs well for the downstream task. Once this is done, a final downstream BiGRU fuses the intermediate representations, and the output of this is then fed through an MLP with dropouts to perform classification. One other idea that we had was to use weight sharing. So instead of using 1 embedding BiGRU per group, we use a single BiGRU, which handles all of the groups. And the intuition behind this is that by using weight sharing, we can capture complete information across the entire tweet instead of cutting it across the hidden layers. Let's now move on and describe the dataset that we used for training the GRUBERT models. Our dataset consists of 2.5 million tweets, split approximately equally between positive and negative, and our dataset is automatically collected and automatically labeled. The labels are generated automatically based on the presence of either a frowny face or a smiley face, which leads to a significant amount of label noise, as we'll see later. The tweets with a frowny face are automatically labeled as having a negative sentiment, whereas the tweets with a smiley face are automatically labeled as being positive. Of course, the emoticons are removed from the tweets to prevent the classifier from using the emoticons as a defining feature. Let's now discuss the issue of label noise. We were able to see during the training process that there was label noise by the following phenomenon. In this chart, we can see that validation loss in black initially decreased, but then started increasing, while validation accuracy was increasing the entire time. And our guess is that this is due to the fact that while the classifier is becoming more accurate, it's less confident about its choices. In other words, the cross-entropy loss is higher. We hypothesize that this is due to the fact that the classifier is overly considering points with an incorrect label, and these incorrect labels are label noise due to the automatic data acquisition procedure, as explained before. To combat this label noise, we apply typical steps such as early stopping and using a voting classifier. This table shows some results of using GRUBERT. The first two entries in this table are typical heuristics of using BERT. BERT last layer refers to simply taking the last layer of the BERT model and using that for training, while BERT last 4 refers to concatenating the last 4 layers and then using that. As you can see, both of these approaches achieve a respectable accuracy. The next 4 models in the table are GRUBERT models. The CAT models are models without weight sharing, and the number represents the number of groups. So for example, BERT Cat 2 is a GRUBERT model with no weight sharing and 2 groups of 6. The BERT share models are GRUBERT models with weight sharing enabled. So BERT share 2 is a weight sharing version of BERT Cat 2, for example. We were able to draw several conclusions based on our experiments of group size. For the BERT Cat models, we found that BERT Cat 2 performed the best, and we conjecture that this is due to the fact that by not sharing weights, we cut the information flow between the different embedding BiGRUs used for the groups. If we use 2 groups, we only have 2 separate BiGRUs and 1 place where the information is cut. In our paper, you can also read that using higher number of groups for BERT Cat models decreased the accuracy more and more. For the BERT share models, we found that BERT share 3 performed the best, and we hypothesize that this is due to the fact that groups of 4 contain similar information and fit well together, while other group sizes contain information that cannot fit well together. Finally, by using a voting classifier, combining various BERT Cat and BERT share models and various different types of pre-trained BERT embeddings, we achieved an accuracy of almost 91%. In conclusion, we saw that by using GRUBERT, we can outperform common heuristics, such as using only the last layer or concatenating the last 4 layers of BERT. We studied different combination strategies, namely different group sizes and using weight sharing or not. And finally, we showed that we can overcome label noise in our dataset via early stopping and by using a voting classifier. In future work, we would like to use different RNNs or transformer architectures for combining the hidden layers, and also try applying GRUBERT to other NLP tasks, for instance, part of speech tagging. Thank you for listening to our presentation.